I'm very happy to have the opportunity to come tell you about this. The story has not a lot to do with Canadian astronomy, nor does it have a lot to do with the continuum work and so on that has been discussed. But it does have a Canadian connection. That would be me. And it does have to do with astronomy. And I think maybe more so in the future than now or in the past, which is why the title is chosen for the way it is. So let's move on. I'm going to talk very, very briefly about the discovery of the 18-centimeter lines, the connection to DRAO, which I've already mentioned. There's an interesting history here, which perhaps some of the younger people in the audience who might be thinking of pursuing something to do with history and radio astronomy might consider this a topic that would be worthy of some examination. The OH emission was discovered in 1963 by my thesis advisor, Alan Barrett. Shortly after that discovery, some of those of you who will remember it, the maser phenomena was discovered in OH. And at that point, anybody who was at all interested in the physics of the interstellar medium went off to try to understand how masers worked. And there was a rather dwindling and ever smaller group of, shall we say, reformers who were trying to apply this technique to understand something about the molecular content of the interstellar medium, because it was the only molecule that we had detected in the interstellar medium, the first one at that point, and the one that was going to be, people thought, a tracer for the distribution of molecular hydrogen in the galaxy. Well, it didn't work out that way because of a variety of historical consequences. One being, I've mentioned, one being the maser discovery, which I would say got a lot of people going off in a different direction. And then in the early 70s, there was the discovery of the carbon monoxide emission, which turned out to be brighter because it was very much higher in frequency, rather easier to observe. And our whole knowledge of the molecular content of our galaxy and nearby galaxies is based on carbon monoxide. Telescopes have been proposed, designed, funded, built solely to observe carbon monoxide emission. And it would perhaps behoove us as physicists trying to understand the interstellar medium to make sure that the carbon monoxide was telling us the right answer. One way of doing this is to try to find a different tracer that would tell you at least an answer that you could relate to the carbon monoxide answer. Well, the fellow sitting about halfway over in the audience there, Miller Goss, who we will hear from before, was the first person who really did an extensive survey of the interstellar medium and carbon monoxide in OH, an absorption survey, and showed that it really was ubiquitous in the galaxy. But I think there's been a very long interval of time between Miller's work in absorption and the emission work. And I want to tell you a little bit about where we are now and where the history might actually take us. So that's what this is all about. And it has to do with dark gas in the galaxy, a phenomenon which has been recently discovered and turns out, I think, to be closely related to OH. So let's go on and see what that. This is the fellow who is responsible for the fact that I'm standing here today. In 1962, I went to graduate school, and I was told by the head of the department that I needed to go and find a staff member to work with, because I had a research assistantship and I had to do something constructive for 16 hours a week. And I went to several people who were working in plasma physics, which is what I was interested in doing. They all happened to be at a conference, the same conference on plasma physics. And the fourth fellow on the list was over in the math department somewhere. And in order to get to his office, I had to go past the office of the third fellow in the list, whose name was Alan Barrett, who had just arrived as a new faculty member and was looking for essentially any graduate student that walked through the door. And I was fortunate enough to be one of those. And he was wanting someone to do some computer programming to get a piece of code working that was going to help him to model the Venus atmosphere. He was on the Mariner Venus projects that NASA was supporting. And so I knew nothing about atmospheres of planets and very little about astronomy at all. Most of my collaborators will insist that that's still the situation. In any case, he was such a nice guy and such an engaging person. So I thought, it's only 16 hours a week, right? It's a job. So I said, I'm going to work for this guy. Well, after working for Alan Barrett for the semester, the fall semester, in the middle of the spring semester, I asked him if there were opportunities that he had for thesis work. And he looked at me, essentially, and he said, "You're a Canadian." Yes. "You don't know anything about radio astronomy." Yes. "I'm going to send you someplace that does, in Canada, because I know you're a Canadian." So he's called John Galt on the phone, I'm sure, although I don't know this particular piece of the history. But he called John, and John said, "Oh, I think I can put him to work," because John needed somebody to write a computer program for them to process the continuum survey of what we now call the Galt telescope that had been accumulating that data. And so I came here to learn radio astronomy in 1963. In the meantime, Barrett was busy discovering OH emission, or looking for it in absorption, I should say. And you can see the discovery absorption spectrum there. And this is just a picture of the principles in that discovery. In 1963, October, Sandy Weinreb on the left, Alan Barrett, Lit Meeks, and Joe Henry at Lincoln Laboratory in 1963. Now, here's an object lesson coming up for those of you young people, perhaps in the audience, who are anywhere near, you do email and you write all kinds of interesting things in your email, and you send the email to a friend who happens to be working in an institution that keeps track of your emails, and suddenly you have a Hillary Clinton problem. Right? Well, so here's my Hillary Clinton problem, because I wrote a letter to Alan Barrett in 1963 after arriving here to tell him about my experiences and what the situation was like. And this letter, the first problem with this letter is that I gave it to a secretary here in this observatory to type, because I wasn't a great typist. Well, the secretary typed it on Department of Mines and Technical Surveys letterhead, which meant that it was going to be for posterity put in some archive. And indeed, it surfaced in more than one place. And I'm very embarrassed about this because Alan was a very easy person to talk to. And so since he had a lot of irons in the fire with NASA contracts and so on, I was greatly impressed. And in order to try to set things in context, I always called him boss. And if you look at it, it says, "Dear boss." And so that's how we communicated. Well, my first view was the one of the Kármán-Costain array. And if you look really closely at the Kármán-Costain array in 1963, there's no wire on those poles. And of course, the summer students were being hired left and right to put wire on poles. I was extremely fortunate because I had learned how to program in Fortran 2, mind you, which we heard a bit about. And I worked in this place, which had air conditioning and was very comfortable. And I was very fortunate to be John's student. Well, I'm not going to spend a lot of time at this because this isn't a symposium on the history of OH. But I had to mention Miller's involvement in it because it's his major survey in 1968 that involves his thesis, which has laid the groundwork for much of what's happening or happened. The extended OH emission from dark dust clouds was discovered in 1971 by Turner and Hylas, and those of you, including Tim, who know Carl Hylas very well, know that he's been a motor behind OH studies for a very long time. But the emission is faint, and it appeared to be limited to large dark clouds in the interstellar medium. And efforts to extend these surveys, it's the only molecule that we had at that moment, the only tracer we had on the large scale in radio astronomy. These were eclipsed in the early 70s by the discovery of carbon monoxide, as I said. There were several unsuccessful attempts to carry out a blind survey for OH emission in the galactic plane. The first one was actually done by Arno Penzias in 1964. That was followed by Knapp and Kerr, who did one in 1972 of a smaller region, better sensitivity. But we now know that the sensitivity of those early receivers was insufficient. And the first successful blind survey for OH emission without looking at specifically dark clouds was done in 2005. I was involved in that with long integration times, hours on end, a 30K paramp at the 25-meter Onslow telescope in Sweden. And that was everywhere we looked, we could see the OH emission. And it's just because the sensitivity finally reached those limits that were needed. And we are now pursuing these blind surveys using the Green Bank telescope and the EVLA. And as I said, OH appears to have an important connection with dark gas in the galaxy. So what's meant by dark gas? Let me try to get this straight. There's three ways we know there is gas out there that does not show up in carbon monoxide. The first one is excess diffuse gamma ray emission that's been shown up by the EGRET, originally the COSB and the EGRET satellite, especially EGRET, and now has been found over much of the sky with the Fermi mission. And what this is because you've got cosmic ray particles which are interacting with whatever's in this interstellar medium, producing gamma rays. And it's the bullets and the targets. The bullets are going to be the cosmic rays. The targets are what's there, right? And there's too much gamma ray emission for what we knew about the targets from carbon monoxide as being molecular hydrogen. There has to be something more. It could be bricks because, of course, the gamma rays don't care what they come from. But it was most likely thought it was going to be a molecular hydrogen component that wasn't showing up in CO. The second one is excess diffuse far infrared emission. This tells us that there's dust out there that we have not accounted for. There's more dust than there is gas that there should be. So if you look at the dust to gas ratios and you calculate from the amount of H1 and the amount of CO that we see, and you say, well, how much dust should there be? There turns out to be more dust there than you get. You get this excess infrared emission. And finally, I'll skip that slide. Finally, there's excess carbon-2 emission from the 158 micron line from diffuse clouds. And those have been found over many regions recently with satellite, in particular the Herschel measurements of the galactic plane. So we know this stuff is out there. We're just not sure what the constitution of it is. So the dark gas is known from these studies I told you to surround all the nearby CO bright molecular clouds and extending into the general distribution of H1. It's not going to likely be high density H1 or encounter, shall we say, all because of H1. People have looked at this, and this is going to be a minor contribution. And the general conclusion is that it's diffuse H2. Now, what kind of physical state? Why should it be there? Well, it's actually pretty easy to understand because the physics of the interstellar medium is all shown in this diagram of photodissociation regions. And while people concentrate on these regions in here, deep in a molecular cloud, actually, this doesn't occupy much of the volume. Most of the volume is way out here. And you'll notice that carbon monoxide is there, and out here we have carbon and oxygen and hydrogen, but no CO. So that's where the dark gas is. And it's essentially everywhere else except for these concentrations where we see the CO. So it's pretty clear that OH is potentially a tracer for this. And we do obviously need an alternative. They're both present in the interstellar medium. Formations are very similar on dust grains. Destructions are very similar. So why should we be seeing OH in places where there's no CO? Well, there's a very simple physical reason for it. And it's got to do with the excitation of the transition. Because it's excited by collisions, it requires a relatively high volume density in order to get carbon monoxide to glow. That's why you see it in the presence of star-forming regions, because it's clumpy and hot. OH exists way out there in the rest of the galactic interstellar medium. And it has an important advantage that way. This just shows you how these carbon plus carbon monoxide and OH actually appear on an excitation diagram. And it's no wonder that OH dominates. H1 is in the same place, and both of them are dominating the low density extended region. So I'm going to show a couple of results now from the last couple of minutes from a survey that we've done with the Green Bank telescope that is, let's see, in this direction in the outer galaxy. It's very lengthy, these observations, so we don't have a lot of observing time yet. We observed a simple grid of 3 by 9 straddling the galactic plane to see what it would look like. This is a blind survey. We didn't actually know what we should find. I'm going to show you then, for these 3 regions, you'll see a set of profiles. They're separated by a ½ degree. And this is the example at 104.5 at latitude of 3. And you can see these are the H1, which we get with the GBT at the same time. This is 1667, and this is CO. And you can see that CO locally around 0 often doesn't appear. There's a little bit here in the Perseus arm there. And we march along because in the outer galaxy, velocity and distance are essentially linearly related. What we have then are these features in H1, and each one of them has a particular correspondence. There's local OH, there's inner arm OH, there's Perseus arm OH, and there looks to be something there we're not quite sure what it is. And outer arm has been, we have detected the outer arm in other. So there is, I think, a new period available to us with using a molecular tracer that we can actually see in any place you look in the galaxy. And here's the example. These lines are all well-behaved, 1665, 1667, the scale difference, so it's LTE. And we do occasionally see funny things. Here's an example. This just shows the angular sizes. Here's an example here of 2 little peaks right there, which don't have anything in. One of them has no H1 counterpart. Well, that's a ringer. We're pretty sure that that's not going to be molecular gas associated with spiral structure. It turns out to be an OHIR star. And those things pop up too because of the sensitivity. So I think we have a potential, a new tracer for the distribution of molecular hydrogen. It's the tracer that is telling us where the so-called dark gas is. And I'm pretty excited about the results. This just shows you what the CO can tell you compared to what, this is carbon monoxide here. All of these dark points are essentially zero. They're all measurements in CO. And the OH measurement is the x-axis. So this is actually much more the independent variable here. And you can see that OH is showing up essentially everywhere, whether there's CO or not. We're continuing this work. Miller's involved, have a graduate student together doing this, and we're pretty excited about where it's going. And I wanted to finally get an opportunity to thank all of the colleagues here at the DRAO who got me started in radio astronomy. Thank you.
Still active.
Oh, yes, yes. Dave is my collaborator at NRAO. Yes.
They really, really wanted to be here to make it happen.
I did my best,
Yes.
Tim.
I tried too.
All right. I have a question. We have a brand new high sensitivity L-band receiver and a 26-meter telescope. Can we do anything?
I think we should talk.
Okay. Good. All right.